So after we shake out some of our logistics and classroom assignments are finalized, we won't have as much to juggle when we get started. This is the first page of the study guide for our first module. And as you look over our module contents, right within the references, that's where you find the study guide. And what's important to understand is that every module is going to have a series of learning outcomes. This is something we covered on Tuesday. And essentially, there are a lot of misconceptions about scientific computing. So as we take a look, one of the ways I wanted to open the class was to share a survey that I had performed with your colleagues last year. So one of the first sessions we had last fall, I asked students to open up their cell phones and participate in a live online survey, because last year, the only modality that the University of the Virgin Islands offered for this course was online. And in order to have regular sessions each week, as a class, they needed to decide which time frame was best, so we could narrow down, a suitable time to meet every week that would serve most student interests. All of that changed this year when the university decided that getting back to in-person classes and offering in-person modalities was very important. And so for the first time in UVI history, CSE 239 was posted on the schedule for a physical classroom, which is why the classrooms we had a suitable classroom on St. Croix, but they had yet to identify a suitable classroom on St. Thomas. Well, all right, so now you know why we just went through some of what we did before we started our session. Anyway, I digress. Whenever you're working a scientific computing challenge, there are data inputs. And one of the things I wanted to do was to collect data from our students, right? Because I wanted to understand their preferences so we could make an informed decision. And that's usually how scientific inquiry works. You have a hunch, or you have an informed hypothesis based on your observations about a relationship in nature, and you have to collect data or information based on that, right? So first we wanted to know what time frame was the best suited, and then we wanted to ask, all right, so then we changed the view of this. And the point I'm trying to make here is you can collect data. And when you collect data, having that on hand is part of the challenge. But then organizing it and representing it graphically so that you can make sensible decisions, the more students that participated, the more data points were collected, right? And why am I sharing this with you? So we had times of the day, and then we had days of the week, right? We wanted to understand, was Monday, Wednesday, Friday a better time frame, or Tuesday and Thursday a better time frame to meet for CSE 239? Did we want longer, less classes but longer classes, or did we want shorter classes and more often? And which time of the day did we want? Because we were doing this all online, we didn't need a classroom, right? The point I'm trying to make is that you can ask for responses and people can provide inputs. But in order to make quick work and come to reach an informed decision or conclusion about it. Half of the challenge is to make decisions about how to represent the data points based on the context. Now, this is a very simple example, okay? Very simple example. But this type of graphic representation of the data is quickest and easiest, and it's provides, you know, an obvious answer, right? Doesn't take long, doesn't take a rocket science to figure out, okay, does the class prefer more Tuesday and Thursday or Monday, Wednesday, and Friday? And in terms of the way the students responded to that question, so we had these series, which time of day is best, which days of the week are best. And that's how we came up with an answer, right? That's something we're going to be doing over and over again in our class. We'll be looking at different scientific and research scenarios, and then structuring a way to proceed to organize our process for data collection. And then once we have, as we're collecting data, what structure or relationships are we hoping to tease out of that data? That's going to help us understand how we want to build our custom applications. Are there any questions about the example I just shared? Going once, going twice.
And exactly what they said.
Yes, what you're seeing on screen are the student responses. So we had about as many students enrolled in the course as we do this year. There were 14, 16, 18 students, something in that order. And the vast majority of them said, okay, we like late morning better. Midday or late afternoon would be a second preference, right? And then these are the days of the week, Tuesday and Thursday. Yeah. Did that answer your did that answer your question, or was that?
Well, no doubt people pick Thursday. Most everyday classes don't have Thursday for some reason.
Right. Yeah, originally the university reserves just after lunch on Thursday for department meetings, college meetings, and university faculty meetings. And that's one reason why you don't have classes around that time frame. So in case you weren't aware. So let's look at a sample of a database, right? So when you start to build a database, you have to make decisions about objects, and in particular, you're creating the structures where that data lives or resides. These are called data tables. And so when you create a database, you're making decisions about the types of information you want to collect. Now, type is a word I use intentionally. Data types, you may be familiar, or you may have heard the term that there are different data types. There's numerical data with decimal points. Those would be called real numbers or floating point numbers. If you have only whole numbers, that's a different data type in terms of databases and applications. Those are called integers, right? Formally, that's one way to explain that. You have alphanumeric. So if I'm creating a new table and I want to design something out of this, I go into design view. I'll call this table 1. I can add a new field called first name, F name, right? And automatically access as a database application or relational database management system, sees the word name in the label for that field, that variable name, and it says, oh, this must be alphanumeric or text-based information. So it assumes that I'm dealing with text. If I put temperature, well, sometimes it's not that intelligent. I have to decide whether I'm dealing with whole number temperatures, right? Whether it's an integer or it's single or double, which refers to a floating point, right? Decimal would commonly be used for financial stuff, right? Every database management system has its own conventions, and every programming language has its own conventions. So you'll hear us use similar or analogous terms instead of saying real numbers. When we're dealing with Python, we're dealing with mathematical disciplines. Numbers that include decimal points are called real numbers, I think. Is that correct? Please tell me if I'm wrong. Did we explain the version numbers for our study guides?
No, I don't think we did, but I typically think I can infer that the version numbers indicate that something has changed.
Yes. So one thing that I wanted to share with you is that before you engage the assessment, after we've reviewed all the material in a given module, when you're ready to take the assessment, one thing you want to make sure of is that you have the latest revision of the study guide. So in this case, if there's major changes, it would be like revision 2 or 3. If there are minor edits for readability and clarity, then we would add a letter, right? So revision 1A, 1B, 1C. I'll typically send these by email, but it's important to understand that before you take the assessment, you want to check what version number and check your email, because sometimes there are updates, especially with reconciliation. In scientific and engineering fields, things change pretty quickly, and it's not uncommon to have to edit a study guide or our course content just because, you know, things are different a year later. But let's go ahead and have a quick look at some of our first objectives. So when you get the textbook, right, if you can read chapter 1, and then when you see sections to, whenever you see references to section numbers like 2 dot something, that's section 1 of chapter 2 through section 3 of chapter 2. I'm just explaining. So there may be on the website, it'll say read chapters 6 through 7, but sections 13.5 through 13.8. And then I get questions from students saying, well, okay, where do I find those sections in those chapters? And the answer is you don't. The whole number is the chapter, and the number after the decimal point is the section. And I know this is more explicit here, but when people get in the weeds and they're in a hurry, they don't always catch that. What is it you really need to be able to know and do if you're a STEM professional? So if you're in science, technology, engineering, or math, regardless of your discipline, what is it that you are supposed to be able to know and do? And right from the textbook here, it reads, a research assistant must know how to organize and to analyze data, as well as how to perform basic calculations, and then to present findings derived from this research in a clear and crisp way. So that kind of tracks with the example I just showed you, where we had to organize and analyze some quick inputs from students. We have to perform some basic calculations, in which case all we're doing is adding some, we're totaling the data. All we're doing is adding the counts so that we get a sum of the choices for each of the choices. And then how to present the findings in a clear and crisp way. And that's really the whole point of this course. Now, one of the things we want you to understand is that sometimes this involves the commercial off-the-shelf software. That's an acronym known as COTS. So when you hear the term COTS, if I say, yeah, that application is a COTS application, I'm talking about something you can buy pre-configured. Applications like Excel and Access. And I just had Access open. In our previous class, I opened up Excel and I said, this is one of the worst ways to organize data. It's just to open an Excel spreadsheet and start typing because things get mixed up. And we'll talk more about that next week. But it's common for neither or for neither Excel nor Access to be ideal. In some cases, the best tool to collect and analyze data is a custom application that you create and that's an aspect of working this process. So I mention all of that to say, when you're doing this, this is the first dynamic that hits. You're making choices about, okay, what tools or applications am I actually using for a given purpose? And a lot of that depends on, okay, what is it you're doing when you present findings? Put another way, has anyone ever heard of the backwards planning process? Backwards planning process?
No.
No. Okay. Well, it's an authentic answer. So if the primary purpose of what you're doing is to be able to present findings, then the big question is, what kind of findings what's the purpose of the findings you're presenting? Efficiency experts call this kind of the next step, right? As you're sitting down to analyze a task, it all depends on the case. It all depends on the circumstances. Let's pretend that you're trying to analyze the mating calls of a given tree frog in the rainforest. Everybody with me?
Yeah, we're with you.
Okay. And let's pretend that we want to use technology to answer those questions. Well, the first challenge is to cleanly articulate, okay, what question am I actually trying to answer here? Is it that I'm interested in how loud or how often the mating calls of a certain tree frog in the rainforest happen? Or am I interested in reporting on what happens based on different environmental conditions, right? Are there things that impair or impede so those are basic questions. You need to start with what kind of output you want. The starting point is actually the end. In backwards planning, you start with the end result. So what's the intent of your research? What do you want to know about tree frogs in the rainforest? Is it that they have a different mating call when other males are present? Is it that, so there's competition, right? And you want to know whether or not when male tree frogs are present, I'm oversimplifying here and I'm using a very kind of off the wall example, but let's pretend there's a lot of males around and there's just a couple of females, as opposed to you have to identify what is it you're trying to get an answer for and what is it you want to investigate. Once you have that understanding, then you can work backwards and say, okay, if I'm counting, okay, if I'm trying to determine whether or not mating calls are different when more males are present, that kind of implies that there's a difference between male and female mating calls, right? Does everybody understand what I'm talking about here? Okay, let me ask the question a different way. Is it safe to assume that a male mating call is different than a female mating call?
Yes.
Absolutely, right? Now, let's just assume that's true for certain animals, that the male part of a mating call is gonna sound or work differently than the female response. Is it possible in some species that the female mating call is the one that presents first? I mean, is it always the male that's always making the first noise? Or is it possible that in some species, the female is actually initiating the exchange? Is it safe to assume that that's different for some species?
Yeah.
Okay. Yeah. So maybe that's not the best example of what we're trying to say here, but you could have audio recording applications off the shelf that allow you to analyze certain aspects of mating calls, right? But then there may be others, maybe that commercial off-the-shelf audio application doesn't let you count the number of calls, right? I mean, you can determine certain things about the mating call, like how loud it is and what frequencies are being used. So the commercial off-the-shelf product helps you do that. But in a practical manner, if somebody's out there and they're putting out their suitability as a mate, right? So I want to let all the female tree frogs know that I'm the best and baddest male in the rainforest, right? Maybe that commercial off-the-shelf application to analyze certain aspects of sound recordings is no good whatsoever when it comes down to, okay, here's one call, oh, here's another, here's a third, here's a fourth, here's a fifth. And in a 2-hour interval, oh my gosh, I don't want to sit around all night counting with what? A chalkboard and a piece of chalk, or a piece of paper and a pen. Okay, that's another one. That's another one. I'm making a mark on a piece of paper every time I hear another one. The point I'm trying to make is that you have to have the proper tool or application for a given purpose. And part of the challenge is to get some definitions about what you want to investigate established up front. And it's only then you can start looking for, okay, what tools am I going to use? And then are there any commercial tools that are available? And then you work backwards from there. Okay, how much do those commercial applications cost? Do I have a budget for my research study? Nope, I don't have a budget. Well, I have to write my own. I have to create my own custom application. So all of this scenario I've taken the time to articulate is an example of the process that is common for people for scientific computing professionals to work through. So if you're a technology professional and you're working alongside the scientist is going to say, well, I really just need to count how many times, I need to count how many times a call is made when the weather changes, like when it's warmer versus colder, when it's raining versus clear, and when there are more females around versus less females around. So I don't need to analyze the content of the calls themselves. I just need to count the frequency or occurrence, the number of occurrences of a mating call, given other criteria. Well, now, okay, let's take that example just for a moment, and then I'll stop, and then we'll move on. What do you need for a sensor to automate this process if the criteria has to do with temperature?
A thermometer.
Exactly. Excellent. Thank you for calling it out. You would need some kind of thermometer, a temperature sensor, a thermometer. And you could have software that starts counting below a certain temperature, starts counting above a certain temperature. So there's a threshold, right? Less than or equal to 70 degrees, less than or equal to 90 degrees. How about for whether it's raining or not? Can anyone think of a simple tool that would help determine whether or not we should turn on or turn off the counts with the microphone? Well, let's see if we can prime the pump here. Oh, how about that? There's an ultrasonic rain gauge. Does everybody know what ultrasound is?
Ultrasound. Oh, it wouldn't it be sound that's loud enough to shatter stuff?
Possibly. It's probably sound beyond our range of ability to hear. That's one assumption. But the truth is you can use sound to determine the criteria of substances, right? So you can use ultrasound to measure the depth of a rain gauge, because the sound that results is going to differ based on the depth in the gauge, right? Now there's a good bit of science in this, but what am I saying? You can get a gauge that's automated that tells you automatically if there's rain, and then you can turn on your microphones, right? And turn off the microphones based on whether it's dry, whether there's rain. And that was just one example. So there's all sorts of sensors and automated things you can do. I apologize for not having perhaps the greatest example. Do we have any biology students in our class right now? I know we do have a lot of College of Science and Math students in this course in particular. Is everyone in the roster, is everyone in this roster a computer science major?
I'm a physics major.
Yes.
Physics major, okay. So who's the physics major again?
Emmanuel.
Aha, okay. I know Courtney is computer science. Thank you, Emmanuel. Ashwin, are you computer science?
Yes, sir.
Okay. James, I think you're computer science. Milan, you are. Omayer, are you also computer science?
Yes, I'm computer science.
Okay. Well,
Yes, I'm computer science too.
I'll check the roster for the rest of the class. Sometimes we have chemistry, biology, and physics students in the mix. And so Emmanuel could tell us about all sorts of sensors that you could use with a computer or a Raspberry Pi in physics experiments. Temperature, force, right? Speed. Does the physics department have anything that can measure speed like radar guns?
I would assume they should.
Right. Yeah, they might. And then again, a lot of our physics faculty are keenly interested in astronomy, right? So they might have all sorts of instruments that measure the frequencies of light or and so on. In any case, yeah, thanks for bearing with me on those points. Just remember, you need to know this definition, and it's really a good way to represent our whole purpose for the course. Is that we're going to spend our time setting the stage, and one of the most important realities of setting the stage is to ask yourself, well, where do I want to be when I'm finished? And work backwards from there. That's kind of an implied reality of this statement. So as you read, now I'm adding that from 25 years of experience in IT, and I've had to work with healthcare and research scientists, and you know, it's an interesting dynamic. And Parsh and Golyev are folk who have published through MIT, and their background is a research science lab. So they're a lot about the experimental method. One of the challenges of working scientific computing applications is to understand the different technology components. For most computer science students, this is a quick review. But in order to perform scientific computing tasks, your hardware has to be capable in a very basic manner. You have to have some kind of processor to do computing. You have to have memory. What's important about the memory is to understand that random access memory, or RAM, does not retain the data or the instructions when the power goes off. So in order for your CPU to function, it has to have a workspace. Think of the CPU as the master craftsman in a workshop. The component that actually gets all the work done. So a CPU could be a master craftsman who is using all sorts of tools and resources to get a job done. That's what the CPU is. The memory would be like the workbench. And the input-output side of this would be the storage bins and shelves, right? So if you think about a workshop in physical terms, sometimes this analogy is helpful. You have only so much space on the workbench, and when you run out of space on the workbench, if there's too much materials and tools on the workbench, the component of that workshop that's doing the work has to make room on the workbench and basically takes some things out off the workbench and stores them in cabinets and shelves, and then pulls other items off of those cabinets and shelves, input output, and places them on the workbench for the. That's one way to look at the physical hardware. Now, why do I take the time to share an example like that? I'm kind of hoping that that example will create an image in your mind that makes this easier to remember. So just remember there are three zones, one that has to do with memory, one that has to do with process, and one that has to do with flow. Why is this helpful in scientific computing? Well, when you're troubleshooting and something isn't working, it's good to start with basic assumptions. You know, do you have enough memory to capture the data? Is your CPU capable of processing the data that's flowing, right? And is the data flowing in and out properly? if you're doing any troubleshooting for a scientific computing challenge that's gone sideways, this is where you start with the troubleshooting. Put another way, you always start trying to solve a problem on the physical layer. So the hardware is often referred to as the physical layer of the technology. And quite often it's overlooked when people are trying to figure out, why is my application, my application is not working properly, and it's all about the software. People are scratching their heads and they're reviewing the coding statements, and they've missed something very basic in the hardware. So that's one reason for including some basic concepts about computer hardware. We just want to make sure that everybody's on the same page. Again, this is very much a review for some of you. You may or may not know, if you're not part of the computer science discipline, that the term bits, when we talk about ones and zeros, the binary data, that's actually a contraction of the two words binary and digits, right? But the relationship between the instructions that are calculations or actions performed on the data, those are represented with ones and zeros, and the data itself is also composed of ones and zeros. But it often helps to, when you're going into a computing scenario, to understand, okay, what are the actions I want to take against the data that I'm collecting, and then what kind of data specifically am I collecting? So it kind of helps to break things down that way. Are there any questions about the hardware components we've just... So if I were to show you this diagram here and talk about the ultrasound, the ultrasonic rain gauge, in which zone would the ultrasonic rain gauge apply?
You mean in the data form, like are you trying to collect the data?
Yeah, if I'm looking at the von Neumann diagram, so this is the John von Neumann model of computer hardware or computer architecture. We have those three zones. Zone 1 is memory, zone 2 is the CPU, and zone 3 are the inputs and outputs. We were just talking about an example where we said there was an ultrasonic rain gauge that was used for the data collection, for part of the computing process. Data collection is the first stage or phase of the computing process with scientific computing applications.
So I would say probably memory.
Well, the results that are produced by the ultrasound.
Oh, then input.
Yes. Yes. Okay, so I started to raise a second question or point about that. Yeah. So the ultrasonic rain gauge is going to be an input. And it's important to understand how components in your hardware that are used to collect and analyze the data, where those fit into this basic model. Because there are specific things you need to do to make sure those are working best. One thing about inputs that's really important to determine is something called sampling. Has anyone ever heard of the term sampling rate before?
No.
No. Okay. Has anyone heard of a time-lapse photograph?
Yes.
Okay. Let me see if I can come up with a time-lapse photograph. So time-lapse photographs are an example of sampling rate. Let's look at some videos. So sampling rate in the world of photography, if you're taking an image, if you're capturing an image and you do it once every minute versus once every second versus once every tenth of a second, sometimes you have changes in your subjects you're trying to capture with the photo, and that subject you are studying changes very slowly, right? So you have a time element that you have to consider, and that's part of your input, right? So if we get back to this, if I have something I'm studying and capturing, and I'm going to compute some data on this, and part of that is capturing an image of it. One of the questions is, okay, how often do I need to capture? If this changes very slowly, I'm going to take a picture every 5 minutes. And then as I play those back faster and faster, I have something that looks like a motion picture, but it has this herky-jerky effect to it. If I decrease the time interval and take more images, the sampling rate is increased, meaning the number of pictures produced and captured for the same time interval is much higher. That's going to incur a much greater overhead for memory and CPU. So that's another consideration when it comes to thinking through the scientific scenario. Now, that's one of the greatest wrinkles for students in this course, and then students in the research labs, is to sort out and organize and identify the specific criteria. So why are we sharing this up front? Well, if you know that this is the model of computer hardware, and you know about the backwards planning process, and you know about the outcomes you want to present information for, then you can use this as a framework to get the process started. The biggest challenge often is just to know, where the heck do I start? When I'm using technology in a research lab, what exactly am I doing, and what resources and tools do I need? And a lot of times it's just a question of getting this information in front of you and reflecting on the context and asking yourself those questions. For our physics student, in astronomy, are we dealing with very large time spans or very small time spans?
I would say large time spans, because like because when I think about like things like astronomy and space like that, because like time passes, well, time is weird in space, but I would assume it would be larger time spans.
I would agree with you. When you're talking about certain topics in astronomy, if you're looking at a galaxy through a telescope now, it took 1 million years or so for that light to travel from that galaxy across space to the point where you can actually see it with your eye and the telescope. And so you're dealing with very large time spans in astronomy. There are cases, though, where you could be dealing with pulsars or other phenomenon where the frequencies and the time sample rates are very small. So that was kind of a trick question. And I want to thank you for being a willing victim for responding to that question. You can have very small time slices if you're dealing with like the periods of rotation, or for certain phenomena, or the periods of pulses for certain heavenly bodies. I know they can be very rapid. It all gets down to, what is it you're measuring and what are the criteria? And time is always one of those things that's in the mix, right? So sampling rate is one of those considerations when you're looking at how to organize and frame what you're doing with the computing technology. So there are things that are mentioned in here that are kind of, it's really important that you take the time to read this and then reflect on it a little bit. This is the process that every CPU performs. And depending on the scientific challenge that you're facing, you may need a you may need a much more capable CPU. Everybody seems to assume that you need the biggest, baddest computer in order to be able to work effective results in a scientific context. That's not true, but one thing you want to understand is that every CPU can only take care of one task at a time. It just does it a million or a billion times a second, and it appears to us that it's juggling all of this simultaneously. That's not true. So there are times where the sampling rate and inputs have to be carefully factored into, okay, what kind of CPU do I have? Can everybody see my screen? Here.
Yeah.
Okay. Does anyone know what the prefix for the metric system giga means? What number does that represent as opposed to mega or kilo? Any takers? So kilobits are how many thousand bits? Oh, shoot.
1,000.
Yeah, I just blew that myself. All right. So what number are we talking about when we say megabits?
100.
Well, that would be centibits. So we have these prefixes that correlate or represent the metric and decimal levels, right?
Would that be a million?
A million, yes. So mega is a million. Again, thank you for volunteering an answer. So when you're talking about 100, that's centa. If you're talking about 1,000, that's milli. If you're talking about a million, that's mega, right? Giga, anyone know what giga is?
That's a million.
Well, that would be,
That's a billion.
yes, a billion. So 1,000 times a million is a billion. And giga is a billion, right? So if 1,000 times 1,000 is a million, and that's mega, and then you have 1,000 megas, that's 1,000 times 1,000 times 1,000. That's a billion cycles. Hertz is cycles, computing cycles. It takes so many cycles to do a fetch, decode, and execute. If you have a gigahertz CPU, that might be a well-suited CPU to perform certain scientific computing tasks if the sampling rate is not so intense. If the sampling rate is intense because of physics, physical phenomenon in chemistry or in physics, you could need a different, you could require a different hardware platform to begin the process in the first place. Now, most of the folks that we have nowadays that work scientific computing applications don't even give this a thought, because hardware has progressed so far and so much in so short a period of time. It's often been said that if cars had developed like computer technology, you could buy a Rolls-Royce Silver Cloud for 25 cents. It would go from 0 to 5,000 miles per hour in a half a second, and it could go 1,000,000 miles on a gallon of gas. And that's one way of comparing, like, okay, here's how automobiles have progressed. Now let's look at computers, computer technology, in particular the hardware. When it comes to the software, that's not true. Okay. What we're going to do is stop here at the end of the, and yes, I go to the trouble of talking about the analogy with the workshop, right? So if my explanation on screen didn't click quite a ways, I really do encourage that you take the time to read through each page of the study guide before our next class. That's going to be very helpful. We'll start getting into the textbook at that point next week. You will have online the first assignments posted over the weekend, so that outside here, listed here under the references and resources, that's where you'll see assignment 1.1, assignment 1.2, and assignment 1.3. We'll also have a companion video or simple instruction sheet to follow for the steps to do that. Any questions before we clear today?
Can I speak with you privately after class?
Yes. All right. Anyone else? I'm going to stop sharing and stop recording.